Hello, 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 hello. Hello, guys. In this video, I'm gonna solve a circuit that we just solved the last video, but with another solution. So in the last video, we solved this, using the node analysis, okay? And we get some answer. Now I'm gonna repeat, solving the problem, but with another solution, with another method, basically. And this method is confusing for many people I know. It is basically using Thevenin equivalent. Okay. So what Thevenin says is that you can like take any two nodes in a circuit. Okay. Like for example, you have a resistance. This resistance has two nodes or two nodes. Just look from the perspective of that resistance into the circuit. So the resistance will see two things. We'll see a source and some reactance if it's like an AC circuit, with inductors and capacitors. Okay. So again, take any like element in the circuit, and you can solve the circuit using that element. Okay. Or by basically by reducing the whole circuit other than this element into two things, a resistor or a reactance in general, and like a voltage source or current source. In Thevenin, it's a voltage source. Okay. So remember in that question here, with that example, I'm going to highlight it again. So we have here a circuit. This circuit it's an AC circuit, has a capacitor with minus G4 reactance, has an inductor with G4 reactance. Okay, it has a current source with a value of 5 angle 30, and it has a voltage source with it's a real. It's a 10. If it's like just 10, this means the angle is zero, the phasor is zero. Okay. So what we're gonna do here, and what we know, what we want basically is IA, this current IA that flows in that branch, IA. Okay, that's what we need. Okay, we solved that circuit, before using the nodal analysis, and we're gonna solve it using Thevenin equivalent right now. Okay, so this current flows into the resistance 3 ohm, the reactance G4. Okay, so if we apply, for example, if we apply Thevenin equivalent, okay, on that circuit by looking from the perspective of the inductor, so basically we're gonna take the inductor nodes and look from its two nodes or terminals into the circuit. We're gonna see a reactance, call it Z Thevenin. We're gonna find a source that we're gonna call V7. That's G4. Okay, these are the two terminals. And then IA here, that flows into through the inductor, will be equal to Thevenin divided by G4 plus Thevenin. Very easy, right? Can we do this using the 3 ohm resistor? Yes, of course, of course. Okay, so here is the resistance, 3 ohm. Here are the two terminals of that resistance. Okay, if we look from the perspective of that resistance like that, from its two terminals, we should also find like Z7 and V7. Of course, different in generally, different from the V7 and Z7 of the inductor. Okay, so we're gonna find again V7. Let's call it V7 dash, just to not to confuse it with these two. And the source V7, let's call it V7 dash, And again, IA is flowing in here, so IA will be equal to V7 dash divided by Z7 dash plus the 3 ohm. Okay. One might say, no, I'm gonna take like the whole branch and look from the two terminals of the whole branch together. Okay, like I'm gonna take this node and that node and look that way. That means we're gonna have the 3 ohm like that, the inductor like that, and we're gonna look like that. Okay. So again, we're gonna have a V7 double dash, V7 double dash. This is Mr. IA flowing the 3 ohm and the J4, and IA again V7 double dash divided by Z7 double dash plus 3 plus J4, the whole reactance. All should give you the same answer. Although V7 generally different from V7 dash, different from V7 double dash. You might find them equal, but generally they are not equal. Z7 dash is generally different from Z7 only, generally different from Z7 double dash. Okay, so what I'm gonna do this one. Okay, and you can check on me and do the other two variants. Okay, you must get approximately, of course, because we have approximations, we have rounding. You should get very close like result. Okay, so let's do that. So to solve like any circuit using like the Thevenin equivalent, we should choose the terminals from which we should reduce the circuit or simplify the circuit into a reactance and a source. Okay, so number one, choose the inductor G4, this guy. Okay, so I'm saying by that I'm gonna have the inductor like that, Mr. G4. I'm gonna look from its two terminals in that way, and I should find, or I should reduce the rest of the whole circuit as a reactance Z7 and a voltage source V7. Okay, and by that, this is Mr. IA filling in here. So IA should be equal to V7 divided by Z7 plus G4. The voltage divided by the total resistance in which the current is flowing through. Good, very good. Number two. The second step is to find basically Z7 and V7. Okay, so they are a little bit different, approaches. Okay, to find, I mean, Z7 has a different approach from finding V7. Okay, so let's find Z7 first. Okay, what we do is we remove the two terminals, the element between the two terminals. We just forget about it. We just remove it completely. Okay, and we put a source that produces a voltage called Vx and a current called Ix. That's what we do. Okay, and we do that on the original circuit, of course, this one. Okay, so these are the two terminals of the inductor. We remove the inductor completely and we put a source called Vx that produces a current called Ix. Good. Then we cancel any independent source. Very important. Independent source. Luckily, in that circuit, we have two sources, a current source and a voltage source, and both are constants. Both are independent. So a dependent source, is a source that its current or voltage depend on another like current or voltage somewhere in the circuit. Okay, but in that case here, let's review this in another video. I'm not touching on that. But here we know the V is 10 volt. Whatever happens in the circuit, it will remain 10 volt. The current source is 5 angle 30. Whatever happens elsewhere, it will remain 5 angle 30. Good. So how we cancel a current source or a voltage source? Okay, we cancel a current source by canceling its effect. What is the effect of a current source? Let's draw the circuit and I'm going to explain on that. So the 3 ohm. Here we have the current source, 6 ohm resistor, Vs, here is Is, minus G4. So, how we cancel Is, the current source? We cancel the current source by canceling its effect. What is the effect of adding a current source in the circuit? It makes the current through the branch in which the current source is located equal to some value, right? So this branch here has a current called equal to 5 angle 30. How we cancel its effect? Cancel the current, right? Make the current zero. Okay. How we make a current zero? Make an open circuit. Make an open circuit in the same branch of the current source. Now we make an open circuit. We make here, we go to draw, we choose the, the eraser, and we make, oh, sorry, I'm sorry, that's too big. No, choose the point. And we make an open circuit like that. Okay, so the current source has no effect anymore. Actually, we can just remove it completely. Okay, like that. So to cancel a current source, we make an open on the current source branch that cancels its effect in the circuit. So the branch in which the current source is located has a zero current because there is an open circuit. Just remove it. In that case, if it's alone, remove it completely. Good. Now, how to cancel Vs, the voltage source? Again, we cancel the source by canceling its effect. That's a voltage source. How to cancel its effect? A voltage source, the operation or the function of the voltage source or the effect of a voltage source, it increases one of its terminals voltage over the other by the amount of the battery or the voltage source value. Let's take an example. If you have a battery like that, called E, that terminal is V1, that terminal is V2. This is a positive terminal, this is a negative terminal. Okay? What is the effect of the voltage source here? It makes V1 minus V2 equal to E. What does that mean? That V1 has an extra voltage equal to E rather than V2 or reference to V2. For example, if V1, let's take E is equal to 5. So V1 minus V2 equal to 5. So if V2 is equal to 0, that means V1 is equal to 5. If V2 is equal to 1 volt, this means V1 is equal to 6 volt because 6 minus 1 is equal to 5. Okay? So that to cancel the effect of a voltage source, make V1 is equal to V2. How to do that? Make a short circuit. Make like that. Short circuit. Because we know if we have a short circuit between two nodes, two terminals, they have the same voltage. The voltage difference is 0. Okay, so this is what I'm gonna do. I'm gonna do like that. Okay, you can even completely remove the voltage source. Let's remove it. Let's remove that guy completely. Okay, and let's make it prettier. So I'm gonna remove that also, and just connect these two nodes together. Okay. That's the circuit from which we're gonna get the Thevenin. Okay, how to get the Thevenin now? Let's get back here. Okay, so look, the Thevenin is we want the Thevenin basically that Vx, this source that we imaginary volt, sorry, this like added source that we added just for the sake of like solving the circuit, it is basically the resistance that Vx is seeing. Okay, so we know that if you have a source and this source has a voltage E, for example, and they produce a current, so the whole resistance is V over I. Okay, so in that case, Z Thevenin is equal to Vx divided by Ix. Okay, that's I'm telling you how to solve it generally. Okay, I know there are other ways, but you're gonna get the same solution, of course. Okay, so we don't know Vx, and by the way, we don't know Ix, but we can get Ix in terms of Vx. So what is Ix? Ix is the current flowing here and then divided here, right? Okay, so I'm gonna draw this circuit in another way. I'm gonna draw this circuit like that. Here is Mr. Vx, here is Mr. Ix, 3 ohm, and here you have two reactances, like in general, a resistance and the reactance in parallel. Okay, how to know they are in parallel? They have the same terminals. First terminal is the same, second terminal here is the same. Okay, so I'm gonna draw it like that. Box called Z, for example, and Z is actually 6 parallel minus G4. So what is Ix here? Ix equal to Vx divided by the whole resistance. 3 plus 6 parallel with minus G4. So Z Thevenin equal to Vx divided by Ix. What is Ix? This guy here. Vx divided by 3 plus 6 parallel with minus G4. I'm not doing any simplification yet. Okay. This guy will go with this guy, of course, and the denominator of the denominator will become a numerator. So that will be equal to 3 plus 6 parallel with minus G4. We are not done yet. So it's 3 plus. Just apply, like if you have two resistances in parallel, R1 and R2, so the whole resistance or the equivalent resistance will be R1, R2 divided by R1 plus R2. So 6 multiplied by minus G4 divided by 6 minus G4, or 6 plus minus G4, which is 6 minus G4. Okay, and then we're gonna use our magical complex number calculator, online calculator, okay, that we show last time. Okay, so we go here and we find that calculator. Should be somewhere around. It's in here. Okay, yeah, we get it. So what we need? So let's put that. Oops, I completely lost it. Put that on the side. Okay, what we need? We need, let's remove that 3 plus. This big term is a fraction term. Put it on a parenthesis. Be very careful when you use this. So we have here a fraction. So put a parenthesis for the first one for the numerator, a parenthesis for the denominator. Okay. So what is the numerator? 6 multiplied by minus G4. Write it minus 4i, because we don't deal with J's here. Okay. 4i. Okay. Which of course minus 24i, but I just like to not to do any sub-calculations, okay, to avoid any mistake. Divided by 6 minus 4i. Again, I still do this like last video. Usually we refer to symbolize the square root of minus 1 as I in all branches of mathematics and complex numbers applications, except in current, maybe except in electric circuits, because we usually call the current I. Not to confuse us, we call it in our electrical engineering circuits J. Okay, but here in this website we use I, the normal or the conventional symbol for the square root of minus 1. Okay, let's review. 3 plus, we have the fraction. The fraction is between two parentheses. We have the numerator, 6 multiplied by minus 4i. Divided by 6. Oh, that's good. So let's just remove these spaces and press click calculate. Oh yeah, we have a mistake here. Let's see. Oh, two consecutive. Oh, yeah. So That's why I'm saying this is very like, so what a parentheses around minus 4i, okay? Because it says that you have like the multiplication, which is an operator, then another operator minus, so it confuses. So put the minus 4i between a parentheses. Yeah, good. So we have it. This is basically the Thevenin. So the Thevenin here, the Thevenin equal to 4.85, because 4 followed by 6, so 6 is greater than 1, so you can round the 4 to 5, minus 2.7. I believe that's correct. J. Okay, good. And if you need the polar form, it also gives you the polar form. You don't need to convert it, but we don't need it. Okay, that's the Thevenin. Now, V Thevenin, number 3. How to get V Thevenin. So let's go back here to our example. So, V Thevenin is basically, before we go to V Thevenin, guys, just one note here. I put the Vx and Ix. You might not find this a lot in textbooks, and you might find like your way to do it is basically to look here and define the equivalent circuit. And the equivalent circuit is 3 plus 6 parallels minus G4. That's basically what we did. Look, the Thevenin is 3 plus 6 parallels minus G4. Okay, but I put the Ix and Vx because this is the most general way to do it. The general way to do it. You can apply this anytime, but to find out the whole resistance or the equivalent resistance just by looking, is not always easy. Here it's easy, like 3 plus 6 parallel minus G4 is easy, but for some other circuits it's not. So you have to put like a Vx, some general like source produces Ix, and the equivalent circuit is the equivalent resistance or the reactance Z Thevenin will be equal to Vx divided by Ix. And you should find Ix in terms of Vx or vice versa, so that when you divide them to each other, they cancel out. Let's go to V Thevenin now. So what is V Thevenin? V Thevenin is the open circuit voltage between the nodes of, or the terminals that you looking in from. Okay, so let's get back here. So we are looking between these two nodes, or terminals of the reactance, or I'm sorry, of the reactance of the inductor or the inductor. Okay, so it is the open circuit between these two reactors. So let's draw the circuit, exactly the same circuit, and put open circuits there. So you have here are the 2 points of the inductor. We have the 3 ohm. We have the current source, Is. Then we have a resistance, 6 ohms. Then we have the reactance of the capacitor, minus G4. Then we have a voltage source, Vs. Okay? And here there is open circuit. Open circuit. What open circuit means? The current here I equal to 0. It's a must. This is a must. And we need the voltage between of this open circuit. If we call this, for example, V1, if you call this V2, let's make V2 ground, by the way. So V open circuit equal to V1 minus V2 equal to V1, because V2 is equal to 0. We ground it. Okay. Usually put a ground. It will make your life so easy. But don't worry. Okay. Good. So if we find V1, then we could find like the V open circuit. Okay. Good. No problem. So let's call this node here. Let's call it VA. Call it whatever. Call it V3, whatever. It's okay. Okay. So what is the voltage across the resistance 3 ohm? Okay. So we have a current flowing in that way equal to 0. So the voltage is opposite because the current flowing from positive to negative, and the direction of the voltage, call it V3 ohm, it's from negative to positive. Okay. So V3 ohm, okay, is equal to the voltage across the resistance 3 ohm. So it is the voltage difference between the two terminals. Okay. So it's equal to the positive voltage minus the negative voltage. The voltage positive is VA minus the negative voltage, which is V1. Good, very good. And that's equal to the voltage difference or the voltage drop on a resistance is equal to the current flowing through the resistance multiplying by the resistance. So equal to I multiplied by 3. But I is 0. So that's equal to 0. So VA minus V1 is equal to 0. That means VA is equal to V1. So if we could find VA, we can find V1, and V1 is our voltage open circuit, and voltage open circuit is actually the Thevenin that we want. Good. So how now we can find VA to find V1 to find Thevenin? Okay. So the most easy way is the nodal analysis. Okay. So we apply the nodal analysis. In the nodal analysis, we search for the nodes in the circuit that has more, that have 3 branches or more than 2 branches, whatever you call it. We have 2 of these. We have this guy here, VA, has 4 branches. Branch 2, 3, 4. And we have this guy, this node. 1, 2, I'm sorry, something happens. Okay, we have this as well. 1, 2, 3, 4. We make one of them ground. We already did. So that's a ground. So we have one node. Okay. Then we apply Kirchhoff current law at that node. Or at the nodes in general. Here we have just one. In that case, here VA. Okay. So let's put currents in any way possible, whatever you like. Okay. So let's first remove the garbage that we did here. Move these, remove. Go back to ink. Okay, we're gonna assume the current is flowing in that way. Let's call it I1, for example. Another current I2, IS, no problem in that, and this is I. The current here is I. Okay, so Kirchhoff current law is saying that the amount of or the rate of or the currents that going into the node equal to the current or the summation of the currents that going out of the nodes. Again, is the summation of the currents going into the node equal to the amount of currents or the summation of the currents going out of the nodes. So what are the currents going into the nodes? We have just one, Mr. IS. This guy is going into VA. Okay, equal to the currents going out of the node. We have I1 going out of the node. We have I2 going out of the node. We have Mr. I, which is 0, by the way, going also out of the node. Okay. So what is IS? It's 5 angle 30 equal to I1. I1, a little bit tricky, so we're going to find it. So I1 is going through the reactance minus G4. So it's equal to, it's going in that way. So that means that's the voltage. That's the positive, I'm sorry, that's the negative, because it's always flowing from the positive terminal to the negative terminal. Okay. So we need to find the voltage across this minus G4 reactance. Okay. So let's call this V, for example, this node here. So I1 is equal to VA minus V over the reactance minus G4. We don't know V yet. We also don't know VA. Let's keep it on a side. Plus I2. I2 is the current flowing through the resistance 6 ohms. So it's flowing in that way. That's the positive, that's the negative. So it's equal to, this current equal to the voltage across the resistance divided by the resistance itself. So the voltage is that node minus that node. That node is VA. The positive node is VA. The negative node is 0. It's the ground divided by resistance 6 ohm. Plus I. I is our friend. Zero. This guy is neutral. Good. We don't need to care about it. It is 0. Now what is V? V here. Okay. Again, if you have a voltage source like that, what does the voltage source do? It raises the voltage of its positive terminal than the voltage of the negative terminal by the amount of the battery or the voltage source. That means if this is, and this is, for example, this is V1 and this is V2, that means that V1 minus V2 equal to 0. Okay. In our case here, V1 is V. In our case here, V2 is basically this one, which is 0. I'm sorry, mistake here. It raises the voltage of the negative terminal by not 0, sorry, by the amount of the battery Vs. In our case, V1 is V. In our case, V2 is 0. And still, our guy is equal to Vs, which is 10 volt, by the way, in that example, 10 volt. So V1 is equal to Vs equal to 10. Now we could know it's 10, it's a given. Vs is equal to 10. Good. So let's do that. So 5 angle 30 equal to VA minus 10 divided by minus G4 plus VA minus 0, it's VA divided by 6. Okay, let's write it again. VA divided by minus G4 plus minus 10 divided by minus G4, which minus will go with the minus, so it's plus at the end. Plus 10 divided by G4 plus VA divided by 6. So let's bring that guy here to the left-hand side and keep VA on the right-hand side. So 5 angle 30 minus 10 divided by G4 equal to, take VA as a common factor, 1 divided by minus G4 plus 1 divided by 6. So VA equal to 5 angle 30 minus 10 divided by G4 divided by 1 divided by minus G4 plus 1 over 6. Okay, what we're going to do right now, we're going to use our magic online calculator tool. Okay, the online like complex number calculator tool to find that. But the best way to use it is to have everything in a rectangular form, x plus gy. Okay, here we have one of the complex numbers we have is in a phasor form, polar form. So we should convert it first. So there is another website that they do that for us as well. So let's use that guy here. I have it. So that's the one that we're gonna use. This is our calculator, but this is not the one that we're gonna use for to convert to the 5 angle 30. This is the one. I'm gonna leave the like the links to these two websites in the description, so don't worry. So the radius is 5 angle 30. Convert 4.33 plus 2.5 J. So let's write this. So that will be 4.33 plus 2.5 J minus 10 divided by J4 divided by 1 over minus J4 plus 1 over 6. Now we are ready. Don't simplify anything. That's our breakthrough, that we don't need to simplify any like calculation with complex numbers. We go to our online calculator and it will do that for us. Okay, so we have here a fraction, numerator and denominator. So 2 parentheses with a slash. Okay, always both parentheses. Okay, the numerator is 4.33 plus 2.5 I. Again, it's I, not J here, because the conventional symbol for the square root of minus 1 is I, not J. But we use J in our electric circuits because we use the I, or we reserve or put the symbol I for the current. So we don't want to have any confusion. Minus, we have another fraction. So put another parenthesis. Okay? 10 divided by G4 or 4I. You can also have another parenthesis. You know, I like to do that to avoid any mistake. Then the numerator, we have two terms. One divided by minus G4. So let's make it wider a little bit. So we have two of these guys, two terms, plus in between. 1 divided by minus G4, put another parenthesis, minus 4I. Then, and put the constant before the symbol I. Don't write it I4. Sometimes this website will translate it incorrectly. Okay. 1 divided by 6. So let's review. 1 divided by 6. 1 divided by minus 4I. Okay. The numerator looks also good. Okay, yeah, looks good. Good. So we have it. We have V7. So V7 or VA. So V7, which is VA, which is V open circuit, equal to 21.48 minus 2.7I76J. Okay, and it also gives it the molar form. Okay, good. That's not the end, because we did that to have like a simplified version of our circuit. So that's our circuit. That's the original circuit. We will simplify it in that form now, because now we have Thevenin and we have Thevenin. Okay, so number 4, step 4, what's the circuit in the simplified like version of it? So we have the inductor, which has the current IA. Our main goal in the question is to find, the problem is to find IA. Here we have the G4. Then we have the Thevenin. Thevenin is equal to 4.85 minus 2.77J, minus 2.77J. And we have Mr. V Thevenin equal to 2.184 minus 2.76J. Good. IA now equal to V Thevenin divided by Z Thevenin plus G4. Again, we don't do any calculations. We're going to use our calculator. Okay. That's our great calculator here. So what is that? Actually, this is basically V Thevenin. So we just copy it. And we open a parenthesis. Always use a parenthesis. Okay, divided by. Okay. Z Thevenin, let's write it. So Z Thevenin is 4.85 minus 2.77 I J plus G4, right? Plus G4, yeah. For 4I. 4I. Because we use I here, not J. Calculate. That's the answer. Okay. So let's write this down. So IA here equal to 4.1 minus 1.6J, which is basically 4.4 angle minus 21. And again, it gives you the angle as degrees, minutes, and seconds. We don't like that. If you go down a little bit, you're gonna find like the original form, the decimal form that we use for the angle, 21.43. Let's compare now. Let's compare. So let's go back to this one. So remember, guys, we solved it in the last video. This exactly the same problem using the node analysis. We should get the same answer, exactly the same answer, or very close to it, right? So here we have 4.4 angle minus 2143. Let's go here. 4.4, 2.145, 43. Very close, right? So basically, that's the correct answer. Okay, guys, thank you very much for watching and see you in another video. Bye-bye.